we discussed that on a high level view, what are all the daemons responsible for the data storage, as well as we discussed what are all the daemons responsible for processing of the data sets. We did not discuss anything high level much. So in detail, we're going to discuss today how exactly a file will be uploaded to the cluster environment, and how exactly a file will be retrieved from the cluster environment, and how the communication happens between name node and the data nodes. Delving deeper into these details, let me initiate the discussion. Perhaps the very first statement that I'm going to make is data is always a pipeline right into the cluster environment. Indeed, the name itself conveys us a pipeline write is nothing but a sequential write. So whatever the data you upload to the cluster environment, the data will be stored in a sequential manner across the cluster. Very important. Indeed, the retrieval is parallel retrieval, as we discussed yesterday. When the data was scattered across multiple disks, the data will be retrieved in a parallel way. So the retrieval is parallel, but the data write is always sequential. And I think we even made this statement yesterday. Replication of the data, where you'll have tree replication by default. So whatever the data you upload to the cluster environment, it will be copied thrice by default. Of course, you can configure this. You can configure that, but by default, whatever the file you upload to the cluster environment on the Hadoop environment, it will be copied thrice by default. This is the default configuration, default replication factor of Hadoop. It's 3. And data is uploaded according to rack awareness. Indeed, before addressing what exactly rack awareness is, I need to talk what exactly a rack is. Let's say we purchased 100 machines, 100 physical machines, and you'd like to manage these 100 physical machines, making them as a cluster. But just imagine making 100 machines. Indeed, managing 100 machines is not a simple task. So we will group those machines under a single namespace ID, placing them in a physical group called as rack. We'll group these servers. I can say, since the servers are rack mounted servers, you'll place them in a physical layer called as rack. So here you can see what a rack is. So a rack is nothing but group of the servers. So these are all the servers. That's what a rack is. So there is something called as rack awareness by default that comes on with Hadoop. We'll talk about this rack awareness within few minutes. And the file details will be present in the name node. So this is the very basic one. So as I specified, whatever the file you upload, the data will be uploaded to the cluster environment in a sequential way. It will make all the 3 copies. And by default, you'll have 3 copies of the data sets. And the data will be stored as per the rack awareness, where file details will be present in the name node. Indeed, the file details is nothing but metadata. This is what we discussed. So let me share you all the details. When I say file details, what are all the details that will be stored in the name node? That's what I need to talk about. So you will have file name, file size, you'll have block size, and you'll have replication factor. Indeed, File name is nothing but with what name you have the data in HDFS. Let's say it is Cisco logs. So you'll have the file name as Cisco logs. And file size, what was the file of the size? You'll have the file size always in form of the MBs. And block size, what was the block size? So by default, you'll have the block size of 64 MB. It's a well-known fact. The default block size of Hadoop is 64 MB, where you can even configure it. So let's say if I make it as 128, it will be appearing as 128. So all this file, whatever the file size, let's say it has of 100 GB. This 100 GB was made into 128 MB blocks. So that's what you have the block size. And you'll have the replication factor. Which is by default 3. And then you'll have timestamp, where it will have when the file was uploaded, as well as it will have something called as modified time. That means when the file was last retrieved and all things. In Cloudera, you'll have, as I specified, if you know on which chunk you have the data set. So if you edit that file, if you edit that chunk, the timestamp will be edited. It's just like touch command. Timestamp. You'll have permissions, user group permissions, and you'll have the user group name. And you'll have block IDs. As I specified, each and every 64 MB block will be awarded with a unique block ID, and that is what the block ID is. So you'll have all the block IDs stored in the name nodes metadata. So all these details will be present the moment you want to upload the file. So let's say if you want to upload a file called as Cisco logs, the attempt you make for the upload, all these details will be entered in the name nodes metadata. Once after the entry was made, then the data will be started storing into the data nodes. Until then, the data will not be stored. Major important point to remember. So the moment when you want to upload the data to Hadoop environment, all these details will be, all these entries will be made in the name nodes metadata. After the entry was made, then only the data will be started storing into the cluster environment. And once after the data was completely stored, once after all these blocks were stored, then you'll have something called as block reports, or I can say block information. Then you'll have block information. Just remember these entire details, whatever I highlighted, will be noted into the cluster environment, will be noted in the Hadoop name nodes metadata the moment you want to upload the file. So once after all these entries were made, then the file will be uploaded. And once after the file was uploaded, this entry will be made later. That means once after all the blocks were stored across the multiple data nodes, each and every data node will be sending some signals to the name node. And those signals will be sent for every 3 seconds by default. I repeat, each and every data node will be sending some signals to the name node, and those signals will be sent for every 3 seconds by default, and we address those signals as heartbeat, where a heartbeat is nothing but the IPv4 protocol which will be sent from the data node to the name node for every 3 seconds. And this heartbeat indicates to the name node that specific data node is still up and running. And every 10th heartbeat, as I specified, for every 3 seconds you'll have heartbeat, and every 10th heartbeat in the sense 30th second beat, will be the block information. where block information indicates each and every data node will be updating to the name node specifying I have these blocks. I have the 15th block of file 1. I have 24th block of file 2. So each and every data node will be updating those signals, and the block information will be constructed through the block information, that is nothing but through the heartbeats. So once after file was uploaded, then the block information will be constructed, right? And remember here, the same copy of the metadata, because as I specified yesterday, the entire metadata comprise of all these details. The entire metadata will be stored in the name node's RAM. And the major part of metadata, that means except the block information, all the other details will be stored even in the name node hard disk, that is in a file called as fs image. It's called as file system image, where you'll have all those details being stored. So these are all the details stored in the name node metadata. And you have these details stored in the fs image. So if you observe, except the block information, everything will be stored in the fs image. Because when the name node got some failure, obviously if it is not a disk failure, while restarting the name node, if it is a partial failure while restarting the name node, whatever the data that was present in the hard disk will be loaded into the metadata again. And once after it was loaded, within 30 seconds, because block information will be anyways sent to the name node for every 30 seconds. So within 30 seconds, it will reconstruct the block information and the metadata will be readily available. If you start storing this block information into the FS image, just imagine making the modifications in the FS image is a tricky task. And as I specified yesterday, one of the challenge is, since we are using the cheap hardware, nodes usually get failed. And when a node was failed, the block locations will all obviously change. So if it keeps on changing, the block information is to be modified in the FS image, indeed in the hard disk, which is a tricky task. So owing to that, block information will not be stored in the FS image, it will be stored in the metadata only. And of course, when the name node was restarted due to any failure, within 30 seconds of time, no need to worry, within 30 seconds of time, you'll have your block information back. That is through the heartbeat. So you'll have all these details stored in the name node's metadata. Very important. File details indicates these are all the details stored in the name node's metadata. And then you'll have, as I specified, the moment when you want to upload a file, an entry will be created in the name node's metadata, that means in the name node's RAM, which will have all these details, where it will construct the block information based on the heartbeats. And as I passed and as I shared just now, FS image will not have the block information, right? And here you can see how a file will be uploaded to the cluster environment. Let's talk about it in a detailed way. Let's say client. So if my machine would like to act as a client for the 100 node cluster, that means if my machine would like to have the privilege to connect to the Hadoop environment, there will be something called as client configurations made on my machine. Point one. This is what we call as a direct to client. Yeah, hello. I'm sorry. So, so a direct client where the machine which has the client configuration, which will have all the client jars present in that to directly connect to the cluster. That's what we call as direct client. And apart from that, let's say you are importing the data from an RDBMS. Let's say you are importing the data from Oracle to HDFS. So at that time, your Oracle DB or the Oracle server, that specific DB database will be acting as the client, where through scoop the data will be imported. When you are ingesting the data from any messaging system, like when you are using something called as RabbitMQ, so RabbitMQ will be acting as your client. So the source is what we call as client, who will be uploading the data. When you are using that as a web server, using Flume, you will ingest the data to HDFS. So that specific web server will be acting as a client for your cluster environment. So you'll have all those details. So no matter whatever the client is, so when the client want to upload the data to the cluster environment, as I specified initially, an entry will be made in the name nodes metadata. An entry will be created, which will have file name, file size, block size, replication factor. It will have block information, user group, timestamp, permissions, block ID, so all the details. Except the block information, all the details as I specified: file name, file size, block size, replication factor, timestamp, permission, user group, block IDs. So all those details will be stored in the name nodes metadata as a first entry, except the block information. As I specified, each and every data node will be sending signals to the name node for every 3 seconds, which we address that as heartbeat. And since name node is receiving heartbeat for every 3 seconds, name node can understand, while when a file was getting ingested, name node can understand which is the nearest data node to the client. Remember, nearest data node indicates not the physical distance. Nearest data node is not at all confined to the physical distance. It is confined to the network responsive time, whichever the node is active in the network. So let's say this specific node is active, so the data will be stored to the nearest data node with the first copy. And imagine and just understand the same block. Indeed, these are all the 364 MB blocks of the file. So the same block will be stored in another node of another rack, because it's a pipeline, right? And the same will be stored in another. So if you observe, you have totally 3 copies of block 1, 3 replications of block 1. Acknowledgement will be sent from last to the previous, and then to the previous, and then to the client, specifying that block 1 was successfully loaded. And then you'll have block 2, and then you'll have block 3. So once after all the files, indeed all the blocks of the file were successfully uploaded, then acknowledgement will be sent from the client to the name node, specifying that the file was successfully uploaded. Now if you observe the 3 replication, whatever I addressed, 3 replication factor, the replication factor 3 is always at the block level, not at the file level. Just imagine, here you'll have all the replications made at the range of the block level. So block 1 has 3 replications, block 2 has 3 replications, and block 3 has 3 replications. And always it is, obviously when I say all the blocks are getting 3 replicated thrice, indeed simply the final file is getting replicated for 3 times. So file 1 is completely got replicated for 3 times. And always the replication will be treated as block level replication, not as a file level replication. And now if you observe, if you delve much more deeper into this, the replications were made in such a way that you have one copy in one rack, two copies in another rack. For each and every block, you're going to find the same. One copy of block 2 in rack 2, two copies in rack 3. One copy of block 3 in rack 3, two copies in rack 1. So you have the blocks copied in this way only. Just observe clearly, you can see that. One copy in one rack and two copies in another rack. You can see that clearly. This is what we call as rack awareness. Making one copy in one rack, two copies in another rack. This is simple, what we call as rack awareness. Right. So now let's talk why we need to load the data according to rack awareness. Indeed, simple. Why we need to store the data in such a way of one copy in one rack and two copies in another rack. What is the advantage of storing this? Rather than this, why can't we store 3 copies in the single rack, or why can't we store 3 copies in 3 different racks? Why can't we follow these 2 approaches? Why should we follow only this blind approach of making one copy in one rack and 2 copies in another rack? What is the basic fundamental concept behind it? Let's talk about it. So let's say just 1 minute, let me open these drawing tools. 1 second. Yesterday I found them actually. Yeah. Right. So in order to address this, I need to share you how exactly a file will be retrieved from the cluster environment. Let's say once after the file was uploaded, client would like to retrieve a file. Let's say this can be a Thrift API, client can be a Thrift API, or it can be any external source, a BI tool which would like to retrieve the things. So a request will be sent to the name nodes metadata specifying the file name. So you'd like to just retrieve some XYZ file. Once after the name node received the request, it will initially verify in its metadata whether the specified file was present in the cluster or not. Let's say the file, whatever he requested, is present. So since name node has the block information, it knows on which node and on which rack the data was stored. So that was because of heartbeats, block locations. So the name node will ask the data nodes directly to serve the data to the client in such a way that it will always choose the rack which has 2 copies. Just understand and just please look into this. The data will be served to the client always from the rack which has 2 copies. That means block 1 will be served from rack 2, because block 1 has 2 copies in rack 2. Block 2 will be served from rack 3 because block 2 has 2 copies here. Block 3 will be served from rack 1 because rack 1 has 2 copies. And it will ask the data nodes, either of these 2 data nodes, which is nearer again to serve the block. Let's say this specific node is nearest to the client, and here let's say this specific node is nearest to the client, and here let's say this specific node is nearest to the client. Now while serving the data, let's say unfortunately this node got failed. Let's not focus what the reason for the failure. The failure could be a disk failure, a power failure, or a data node service failure, or even a network failure. So irrespective of the issue, root cause of the problem, let's say simply the node 2 of rack 3, whichever is serving the data to the client, was failed. So immediately the connectivity will be shifted from this node to the very next node on the same rack, wherever it has the same copy. So immediately the connectivity will be shifted from node 2 of rack 3 to node 1 of rack 3. Immediately. And let's say while even serving, the rack entirely got failed. Then the connectivity will be shifted from this rack to the other rack, because you have the copy in the other rack, and this rack will be serving the data to the client. And all these racks will be connected through the rack level switches, where usually they'll be using Cisco switches. Here of 24 port switches, there'll be some switches where they'll be using those switches. So using those switches, they'll be connected to the other level rack. So this is how a file will be retrieved. And if you observe here, simply always the node level connectivity will be faster than the rack level connectivity. Point one. So here, since it is choosing the rack which has two copies, when the specific block was down, when the specific node was down, the connectivity will be immediately shifted from this current node to the very immediate node of the same rack. And the client will not experience any downtime, or the client will not experience any delay time or delay response from the cluster. It will be instantaneous, because always the node level connectivity will be much more faster. And if at all there is a rack failure, then the connectivity will be shifted from this rack to the next rack for the higher availability of the data. But just imagine if you make all the three copies in one rack without following the rack awareness. I hope whatever the modifications I'm making is clearly visible. So if you are making all the three copies in the same rack, obviously you'll have very instantaneous output to the client. You can serve to the client instantaneously, because always it will be a rack level connection. But what if the rack level gets failed? So since it is a node level connectivity, always the nodes will get connected and the data will be served to the client instantaneously. But what if the entire rack was failed? So obviously there is a hazard of losing one of your block from the file. That's not a right approach. Now let's come to the second approach, making three copies in three different racks. Like this. So let's say this is serving data to the client, this is serving data to the client, and this is serving data to the client. And any one of the node got failed, the connectivity should be shifted from this rack to the other rack, and then from that rack the data has to be served. Where, as I specified, always the rack level connectivity will be a bit late. So obviously there will be a delay response to the client. So owing to that, they came up with a solution called as rack awareness, where they made two replications in one rack and one replication in another rack. That is what we call as rack awareness. I hope I'm clear till enough. Please let me know if I'm not. Right. So let me just.
Sorry.
Yeah, please.
Yeah, I have one question. The clarity wise is very clear. That's no problem at all. I had one question. If you're saying it's all sequential when it's loading, there will be millions and trillions of records, right? So will it not be very slow, or is that expected? And
no, because just let me share you whatever the network speed you have on top of the environment is almost 10 Gbps.
Oh, okay.
10 to 16 Gbps. They'll be connected through a high-speed network always.
So that
So
shouldn't be a problem, yes.
yes, passing hardly few MB of data, because hardly you'll be making a chunk of 64 MB or 128 or at most of 256 MB chunk. So passing those chunks of data across 10 Gbps network will never be a problem, and it will be made instantaneously. You will not even experience it, whether it was loading sequentially or whether it is loading parallelly. You will not experience that because at the high speed networks.
Okay. I have one more question.
Yes.
The details of this, right? Like the
Uh,
node configuration and the communication between the node and the client and all this. I mean, is this useful for as an admin or even developers? I mean, of course, we
no,
should
no,
know what's happening in the back end and how the architecture is and all that. But while
dev,
programming
yeah.
will we be having should know that which node the data is and which rack the data is?
No, no, no.
No.
Even administrator will not know on which node the data is,
Okay.
because it's completely managed by the name node. It will consider the load balancing, because name node will know how much disk space is available regarding the disk usage of each and every data node. The name node will know all those details. So basing on the disk usage, the data will be stored across the cluster.
Okay.
And administrator will not know on which node the data is.
Okay.
But if he want to retrieve it, he can run a command called as fsck, file system check, which will display on which node it has the data and all the stuff. And being a developer need not to know on which node the data is and whatever the protocols that were being used. So he need not to know about it, because developer's job is to process the data sets. He will not be uploading the data. So once after the data was populated, developer's job comes into the picture while processing it, while analyzing it. So
Computing
he'll
it.
be designing a Mapreduce job, so to perform all those actions. Hardly he can use any sort of scoop imports or flume imports, only at that level.
Okay.
But to
And
understand how exactly
maybe the developer needs to know from which cluster. I mean, if there are some multiple clusters, then we just have to know which cluster what is stored, right? Or not
obviously,
even
because
that.
when he want to connect, when he
Yeah,
want
yeah.
to connect to the specific cluster, he need to give the port UI.
Okay, okay.
He need to give the port numbers, and for that, he need to just know the IP address, all the stuff.
Okay. So only to that extent is good enough, I think,
That's
right?
it.
Okay,
That's
okay.
it.
Got it. Thank you.
So once after the data was uploaded, this is how a file will be uploaded to the cluster environment, how a simply file will be retrieved. Now let me address about an important discussion. Perhaps I can assure that will be even interesting and very important indeed. I'm sure majority of us might have worked on top of Unix environments several times, where everyone knows that the block size of Unix is 8 KB. Let's say that you uploaded a file of 10 KB on top of the Unix file system. So when you want to store this 10 KB file, obviously it's gonna consume 2 blocks, where it will have one 8 KB block, and in the other 8 KB block, it's gonna consume 2 KB. So one complete 8 KB will be occupied, and only 2 KB will be occupied from the other block, and remaining 6 KB, it's a well-known fact, it will be wasted. It will not be utilized, confined to a file. Let me talk applying the same rule on top of Hadoop environment, because 8 KB or 6 KB KBs will not matter. But let me address what happens on top of Hadoop environment, where you want to upload a file of 100 MB. Example. So it will have 2 chunks. One 64 MB chunk, and the other is 36 MB chunk. So 164 MB will occupy the complete 64 MB block. The complete 64 MB block will be occupied because of the first 64 MB split. It will be completely occupied. 36 means Some part of this will be occupied, where 28 will be still available. 28 MB will be still available. What about this 28 MB? Will it be wasted? If yes, definitely we're going to lose huge disk space because of these wastages. And that was quite fortunate. It will not be wasted. It will be utilized by another file. Let us discuss how it will be utilized and how exactly the data will be stored under the disk. Let me talk about it. So, point one, Hadoop is not an operating system, a well-known fact. So we know that Hadoop is a framework which will be working on top of Linux or Unix environments. So let's say you purchased 100 nodes, and prior installing Hadoop, let's say you installed Unix on all your 100 machines. The moment you installed Unix, the Unix file system will be accumulated on top of the hard disk. So you can see the thin black lines, where these thin black lines are nothing but the 8 KB blocks. So you have all your 8 KB blocks stored across the cluster. Across the disk, all your 100 disks, you'll have the 8 KB chunks made by. And once after the 8 KB chunks were made, once after you install Hadoop, you'll have the Hadoop distributed file system, indeed the 64 MB blocks overlapping on top of your Unix file system, like this. Now, let's say you'd like to store your data, a data of 100 MB as I shared. So we know that 164 MB block will almost equal to 8008 KB blocks. These are all the 8000 blocks. These are all the 8008 KB blocks. And we even know that the data should be finally stored on a mechanical device, nothing but disk. So it is the EM device. So the data will be stored finally on the local file system only. Whatever the data you upload, the data will be finally stored on the 8 KB file system, underlying file system, or we'll say simply operating systems file system. The data will be stored finally on the operating systems file system, nothing but the local file system. And only the indexes of those millions of blocks, or I can say thousands of blocks, will be stored with the 64 MB chunk Hadoop block. The moment you want to retrieve it, the disk head need to be moved across these 64 MB chunks, because it already had the addresses of all the things. So it will pull up and it will give the data to the client. So the disk head need to be moved across the 64 MB chunks. That's where we got the advantage of the disk seek time. So now, when you upload a file of 100 MB, one complete 64 MB block will be occupied. That means all the 8000 blocks will be occupied. And remaining 36 MB, some part of the 64 MB will be occupied. That means, let's say, hardly it occupied something like 4,500 blocks or something, 5,000 blocks. So remaining 3,500 blocks or 3,000 blocks, along with other 4,500 blocks, gonna create another 64 MB block. So it's cumulative. So you'll have a 64 MB block here, you'll have another 64 MB block here, and you'll have another 64 MB block here, and at last there might be some space of the disk, there might be some small space of the disk which will be definitely less than 64 MB. Hardly it can be 63 point something MB, which will be wasted, which could be wasted, or even less than this. At most it can be of 63 point something MB, which will be wasted, which could be wasted. So except that, almost the entire disk will be utilized in a perfect way. because the data was getting further chunked into the 8 KB splits. And the data will be finally stored in the local file system. Very important. Only the addresses will be stored on top of the HDFS. So indeed, I can say simply, it will act as a virtual file system on top of your local environment. So that's how it will make the best disk usage. Right? So this is how internally the data will be stored on top of the Hadoop environment. And here, this is what we discussed so far. Name node will have the metadata, maintains all the metadata details, and it will look after the data splits, because name node only knows on which node you have your data available. So it will be taken care by the name node only. Name node only knows that. And handling the node failures, this is what I need to talk about it. I think yesterday I passed a bold statement stating that everything is almost automated on top of Hadoop environment. Let me share you why I passed that statement and how Hadoop can handle the node failures. Let me address about it. So as I specified, each and every data node will be sending some signals to the name node for every 3 seconds. This is what we discussed. Each and every data node will be sending some signals to the name node for every 3 seconds, which we addressed as heartbeat. So the significance of heartbeat is the 3-second heartbeat intimates that the specific node is up and running. Let's say name node could able to receive heartbeat from all the data nodes except this specific data node. Except the specific data node. And as I specified, again, let's not talk about what was the root cause of the failure. It can be a power failure, disk failure, or a network failure, or you might have something like data node service failure. So irrespective of it, name node cannot receive any heartbeat from this specific data node, and it can receive heartbeat from all the others. So the moment name node recognizes that the specific data node is not sending any heartbeat, name node will consider that the specific data node was down. And since it already had the block information, it can easily understand what are all the blocks went on under replicated, because default replication factor is 3. So if you lose one of the replication, it is 2 replicated, which is under replicated. It will internally arise an exception called as under replicated exception, and name node will know which blocks went on under replicated. And even from the same block location, it can understand these 2 data nodes, specifying the under replicated exception and to go on with the other copy. So the block 2 will be made as another copy either in this rack or in this rack, because it will again follow
Hello.
something that the name node will send a signal to either of these data nodes, either of these 2 data nodes, specifying the under replicated exception, mentioning that the specific block was under replicated because of a failure, and the block will be made, whatever the block was lost. So the block 2 will be made in either of these 2 racks, either in rack 2 or in rack 3, according to rack awareness. So again, it will ensure that it will always follow rack awareness. So let's say it made here. So now you can observe you have totally 3 healthy replications. So it is automated. Even administrator need not to worry regarding the failure. So it's completely automated on top of the Hadoop environment. This is how NameNode will handle the failures. It's by default. Handling the node failures, and NameNode will not be a bottleneck. Just observe. If you observe again from the beginning, you can clearly see that once an entry was created in the NameNode's metadata, the data was directly getting stored to the data nodes. And NameNode will not be involved in the data storage. So the data will not pass through the NameNode. The data will be stored from the client directly to the data nodes. Because if the data has to be passed through the NameNode, there will be millions of writes. So at that time, definitely NameNode will become a bottleneck. So the data will be always stored directly to the data nodes like this. And above all, the last one, since it's a drawback, I mentioned it at the last. So it's a single point of failure. Irrespective of the cluster size, whatever you have, whether it can be a single node cluster or a 10 node or a 15 node or a 2000, 20,000, 50,000 nodes, when your name node was down, you cannot access your data sets. Of course, you might have had your second name node using which you can reconfigure a name node, but in order to make that reconfiguration, it will at least consume 30 minutes, and during these 30 minutes, your cluster will be a downtime. So it's a single point of failure. And owing to this, in order to eradicate this single point of failure, in the latest, in Hadoop 2, they came up with something called as name node high availability. So you can have n number of multiple name nodes. We'll talk about that as well in the upcoming discussions. So this is how you can see that. And what do your name nodes metadata comprise of? This is what we discussed just a few minutes ago, which will have name of the file, splits, permissions, timestamp, block locations, and all the things. And entire metadata will be stored always in the RAM, where it will build the block information through the heartbeats. This is what we even discussed. So through the block information will be always built through the heartbeats, where a heartbeat will be sent usually for every 3 seconds. For every 3 seconds, a heartbeat will be sent to the name node, and which will look after the data replication based on the malfunctioning. It will look after the data replication basing on the malfunctioning, where if any one of the node get failed, so in order to resume that, in order to make your node back, in order to make your replication back, the name node will take the privilege of making another replication, another healthy replication over your cluster. And this is how you can see all your data nodes sending signals to the name node. And the significance of heartbeats are like this, that they will talk about alive or dead status, block information, available space, where the heartbeat will be addressing about the alive or dead status, block information will be sent as a 10th heartbeat, and available disk space. So all these details will be sent to the name node. And once for a disk, once for a node, if 80% of the disk usage were full, name node will pop up with a message to the administrator, where the administrator need to attach one more node to the cluster environment. So the cluster size, or I can say cluster installed capacity, will be elasticized so that it can host for more magnitudes of data sets. So that's how we have the discussion. So we discussed today how the communication happened between name node and data nodes, how a file will be uploaded, how it will be retrieved back, and what exactly rack awareness does. And we spoke about how name node will handle the failures of the data nodes. And tomorrow we'll talk about the communication between a name node and secondary name node. Remember, always the communication happens between name node and data nodes, and name node and secondary name node. Secondary name node and data nodes will not talk to each other. Secondary name node and data nodes, there will not be any communication between them. Only the communication will be between name node and data nodes and name node and secondary name node. We'll talk about the communication between name node and secondary name node tomorrow, and then we'll talk about the Mapreduce part, how exactly the data will be processed, and day after tomorrow we'll talk about how exactly the data will be processed in a detailed manner. We'll delve much more deeper on top of it. And after 2 days, we're going to build the cluster on your machines. Right? Any questions so far or anything unclear? Please kindly let me know, where you can shoot me with your questions.
Hi Vignesh, can you go to that file system import screen, like where we discussed some blocks like B1, B2, B3?
One second.
Yeah.
So you're talking about this, right?
Yeah. So here,
Yes.
let's suppose if the name node fails, so
Name node field or
if the name node fails here, so what will happen? Like,
okay.
will it make so yesterday we talked about some screenshot, like the data node will take a screenshot of the name node, then again we'll configure the name node.
Secondary name node. Secondary name node will take the snapshot of the name node.
Okay.
Secondary name node will take the snapshots of the name node's metadata. Name node will not take any snapshots.
Okay.
So the data nodes will not take any snapshots.
Okay.
Name node's metadata will be taken as a snapshot with the secondary name node. Secondary name node preserves the snapshots always. We'll talk about it, how the snapshot happens in all the details. Tomorrow we'll talk about it.
Okay. The other one is like the terminology wise, like can I say rack as a cluster? I mean, the cluster is a rack.
No. A cluster will have a group of racks.
Okay.
So a cluster is an entity, and a cluster will have group of racks, where a rack will have group of nodes. Simple that.
Okay.
So the basic unit functionality is a node to rack under a single namespace, and a rack to the cluster. That's it.
Okay. So cluster is basically a machine, or what exactly?
No, cluster is nothing but group of your machines.
Machines.
Let's say you have 100 machines, and connecting them across is nothing but a cluster. So you have a 100 node cluster. 100 machines grouped together is nothing but a cluster. Yours is a 100 node cluster. And in order to manage all your 100 machines in a better way, we are grouping them further, nothing but as a single rack.
Okay.
Catch the point?
Yeah, got it. And also each rack is there any size limit for the nodes? Like this rack should be this number of nodes, and like...
That depends on the rack level switch, whatever you use. So
Okay.
rack level switch has how many number of ports, those many number of nodes can be connected to that specific switch. So you'll have something like 24 port switch, or you'll have something 48, 54 port switch. There is a different ports available. So basing on that port, you'll decide how many servers, or I can say how many nodes can be placed in that specific rack.
Okay. Coming to the other question, each rack has a B1, one rack 1 has a B1 and the rack 2 has a two B1 blocks. So is it a random way, or is there any system to generate, like the rack 1 should have only one B1 file block and the rack 2 has a two B1 blocks, like that?
I have some confusion in your question. So let me share you. You mean to say only B1 should be stored in rack 1, and the other copy should be stored in rack 2?
Right.
Or is that your question?
Yeah. No. Is it a random way, like that we store the files? Or?
Let me share you. Let's say there can be even a chance the data can be stored block 1 here, and the remaining two copies can be stored here also. But definitely you need to have two copies in one rack. Two copies should be stored in one rack. That can be the consecutive rack, or can be any other rack.
Okay.
Catch the point?
Yeah, got it.
Yeah.
Vignesh, I have one question.
Please.
You said the heartbeat will be sent every 3 seconds, right? Will the block
Yes.
info has to be sent as well each time?
No,
At
no,
the
no.
30th
Only the
second?
10th heartbeat. Only the 10th
10th heartbeat?
heartbeat. That is nothing but 30th second beat will be sending the heartbeat. Only the remaining 3 seconds heartbeats, the frequent heartbeats indicates that the specific data node was up and running, and it will intimate the network responsive time. Only that.
Yeah, but what is the need? Because once you write once, read any number of times, right? So once you write, then why you have to keep getting that information? What is the necessary to send an block info every 30th second, right?
Because
Heartbeat I
because
understand, because you need to failover shouldn't happen.
So let me share you, if at all, if any failover happened at once. So once the replication will be sent to the other thing. Let's say this specific block was failed. This specific block was failed. Node was failed. So block 2 was copied here. How does name node update this information if there is no block information being sent?
I thought the name node gets updated only after the block information is being returned fully. So if it had failed at N2, then N2 wouldn't have returned in name node at all. N4 will be returned, right?
Sorry?
If the name node gets updated only after loading the data
between N2 and name node, right?
Yes.
So now, please.
Basically, what I meant was, if the load data was failed in N2, it didn't even complete. It will try in another node, that is N4. So
no, I'm not talking about that. I'm not talking about that. Let's say after the data was completely stored across the cluster.
Oh, across the cluster. Okay, I got it.
Across the cluster. Then, if the specific data node was failed, how that modification will be updated in the name node?
Yeah, that's correct. Yeah,
right.
Thank you.
For that, it always makes for 30 seconds beat.
Okay, got it.
And as you mentioned, while writing itself, if the node was failed, then obviously the connectivity will be redirected to the other node, because acknowledgement will not be sent.
Yes, correct. Yeah, okay, got it.
Block, for each and every block upload, there will be an acknowledgement. So acknowledgement will not be sent to the client, because last it should be a sequential acknowledgement. So the two-layer acknowledgement will not be sent. So obviously it will look for another node to make the replication, and then the replication will be completed.
Got it. Thanks.